And you can use the order.
Now hang on, the camera's on.
Do you want to remove this?
Yes.
Visualize or just nothing?
Nothing. Thanks.
Yeah.
Right, guys, how nice to see you. Shall we just have a party?
Oh, well, guys, management for taking you here. Enjoy.
What sort of party shall we have on these times? Remote snobbing or something like that? Drinking through 1 meter straws? Oh, fun games. Right, it's the last lecture. It's the last lecture I'm giving you. Anybody going to lecture tomorrow? No. Any more this afternoon?
Last one of the year.
Last one of the year. We shouldn't really be working, should we? We should be playing. But I'll do my best to entertain you because we've got to get on. Right. Last week we discovered the logic function as a model for a neuron. And we got quite excited because it has some very interesting properties. Huge advantages over those stupid methods that came out of America 70 years ago. So the basic structure was, and these methods are targeted mainly at pictures, but you can use them for any other data form as long as the data form is the fixed format. So let's go to the picture example. We have an input. Exam questions likely to be 3 by 3. Real problems 512 by 512, or if you've got high resolution 4000 by 4000. Principle is the same. This is the input. And the processor is a set of logic functions. And the logic functions, I'll draw 3 of them. Oh, how nice it is to write on a black or whiteboard. These are logic functions. They will have outputs, F1, F2, and F3. They go into a summer. And we have the option of a threshold on the output. And there is my response, as Kurt said. Right. The logic functions have to be connected to the picture, the input space, and that is called the mapping. And unlike an analog network where you connect every pixel to the first layer, here we are taking subsets of the picture going into the logic function. And these subsets are called n-tuples. Why n-tuple? Because it's n pixels. In this example, I will use n equals 3 because it is convenient, but that is a system parameter. And the system behavior will change as you change n. We have to connect the functions. Each will now have 3 inputs to the input space. And so it's easy to follow these simple examples. I will have a mapping. It's called mapping. And initially I'll go row by row. And if n equals 3, and it's a 3 by 3 image, then if I'm taking row by row, this is looking at the pixels in the first row. This will be looking at the pixels in the second row. And this will be the pixels in the bottom row. There we are. And so this is the n-tuple. That's the mapping. And to implement these functions, and the functions will change with training, that's where the learning takes place. We're going to implement these functions not in discrete logic, which was done 50, 60 years ago. We're going to use memories. So if I have a 3-input function, and I want to implement it in a memory, a read-only memory or a RAM, how many memory locations do I need? 3. How many states on 3 inputs? 8. 8! And let's divide these into 8. Each cell is a 1-bit memory. Originally that would have been a DFF. And if you count those up, or if you're more sophisticated and you can multiply 3 by 8, you will come to the conclusion that this network is using 24 bits of memory. And the addresses, let's put the addresses here, starts off with address 0 right the way through to address 7 in binary. So we have 0, 1, 2, 3, 4, 5, 6, and 7. I've got that applies to all 3. So that is the basic structure. Now, why this is interesting, we're producing logic functions which will allow variability, choice at the interval. If I was just taking a single pixel and the information was binary, I could only make 2 decisions. It's white or it's black. And if you have a 26th class problem, such as recognizing characters, or a 50 class problem recognizing your faces, can't really make a decision on 1 pixel. And that was where the Browning and Bledsoe method came in. Way back, it was a software method. It wasn't really pretending to be a neural network, but it allowed choice and variability at the interval level. And the beauty of a logic function, unlike the McCulloch-Pitts neuron, once you've trained a function on a pattern, supposing the inputs here are 1, 1, 1, let's call them A, B, C. Supposing the picture here we'll start off with all zeros as it is. If I want to recognize all zeros in the top row, this function here, it needs to be F1 equals not A and not B and not C. Which means if 0, 0, 0 appears there, I get a 1 out there. Pretty basic logic stuff. But the beauty is of this method, if I put in another pattern in there, cross is 1 and dot is 0, allowing on the top row 0, 0, 0, or 1, 0, 1. I can take that same function, I can change it, I can now recognize the current interval, but I don't lose the response to the previous one. And the function becomes, it was not A and not B and not C. If I make it not A and not B and not C, or A and not B and C, it will recognize both. And in terms of the hardware, there's no searching, it's just an access to a memory. It doesn't matter whether I've got 20 terms in the function or 1 term. It's parallel access. Each access takes the same time. Does everybody understand that? Because that's an important property. Am I insulting your intelligence? It's so simple. Yes? Not quite. Okay. So that's the principle. Now, if the network, if the interval was the size of the input, let's call the input space capital N pixels, if little n equals big N, I would just have 1 function, and that would have 9 inputs. But as a learning system, that would be NBG. We know what NBG is, don't we? We know what NBG is. No bloody good. Why? Because then it would only recognize the training set. All the terms in that single function, if it were a single function 9 inputs, would be the training pattern. It would only ever respond to the training pattern. It would act as a memory, fair enough, but it would not generalize. And in artificial intelligence, you need generalization. Because whatever method you're using, You never use exactly the same data. You think you do as humans, we perceive it to be the same, but my face can have millions and millions of versions. Size, position, lighting, incalculable variation. We've got to generalize. So that's the tricky bit. Right, so that's our structure. Now the properties. I want to go over a couple of properties today. First of all, well, the input depends on the resolution of the function. We can choose n. How does n change the behavior? If I went from n equals 3 to n equals 4, I would only have two functions of 4 inputs, and 1 pixel would be left over. If I went down to 2, I could have 1, 2, 3, 4, 4 pixels, 4 functions, and again 1 would be left over. The missing pixel at 3 by 3 could be vitally important, but the missing pixel at 4000 by 4000 resolution is undetectable. With your latest iPhone 13 that you just bought, I bet there's a couple of dead pixels on the 4000 by 4000 and you'll never know. So n is a system parameter. The patterns you train the system on is another system parameter. The threshold that you set is another control system parameter. And of course, the way you connect these up is will change the behavior of the system. Now, I've taken row by row. There's only 3 ways of taking row by row. But how many different ways can I select the mapping for 9 by 9, or 3 by 3, 9 pixels? How many different mappings might there be? Well, how many choices would I have for the first connection? 9 pixels. Could I choose one of them? 9. So there's 9 ways of taking the first connection. I don't want to overlap. How many ways of getting the second connection? 8. Independent, multiply them. 9, 8, 72 ways of getting 2 samples. Third one? How many mappings in total? Go straight to the answer. 9 factorial. What's 9 factorial? I think I worked it out once. 362,880. Bloody hell! Actually, it's not quite that because the order of selection of pixels within the interval gives the same effect. But that's still a huge number. Big data again coming to bite us. 36,000 ways of selecting these 9 wires for that 9 inputs. Now think back to the McCulloch-Pitts neuron. You only have one way of wiring it up. And if we've got an immense number of ways of connecting the system, and some are better than others, then we have the possibility of optimizing and tailoring the system to the best solution. Added flexibility that the analog neuron doesn't have. Right. So, what I want to deal with first of all, let's take the mappings. Let's check it up there. Before I go into the mapping, actually, let's just look at state space. Or pattern space, I should call it. For the analog network, you should know in 2 dimensions, which is the only one we can easily see. The weight vector defines the decision surface at right angle to it. We have 2 clusters. If we get the decision surface to separate the 2 clusters, then we've got the weight vector. We then use the weight vector and get the scalar product as tough sample patterns. And depending on whether the test pattern is positive or negative, we've got a 2-class classification. When you start off setting up an analog neuron, you choose a random weight vector. You've got to start somewhere. The system's got to be Immediately you've got a weight vector, you are cleaving the pattern space into two classes. And what the training does is try to adjust the surface to get the right answer. So in day one, in operation one, with an analog neural network, you get 50% generalization for one class, 50% the other. And of course, initially it's random, it's meaningless. Now, the pattern space model for the digital net is very different. Let's draw a block and call that the universe. U. And let me take one training pattern. Let's call it there. And there's a two-dimensional representation of what is a multi-dimensional real-world problem. One pattern. It could be the pattern going in there. Let's go back to the T that I had in the last lecture. Right, so that T is a 9-dimensional binary vector, but I'm representing it, I'm regarding it as a point in this space. If I trained that network on the 1T, how many patterns would it recognize? Just the one. Again, an NBG condition. It's not doing any use. Right. If I take a number of patterns, in the previous example I took 3 patterns, they will be at different points, different crosses, and let's call that the training set. And let's call that for the letter T, T subscript T. The system will recognize those 3 patterns. Yes, we have a threshold of maximum yes for real ones, the summing gives you 3, a maximum X has a sum of 3, the threshold is 3, we're recognizing 3 patterns. But we also recognize other patterns. We saw generalization last week. So on the basis of those 3 training patterns, there will be a generalization set. And let's call that GT. It will include the training set. The training patterns are always in the generalization set, but it will include other patterns. And in the case of the T's I gave you in the last lecture, there were 3 training patterns, and each entable had a choice of 2 allowable states, and we ended up with 8 patterns that we recognized. So the 3 patterns were the training set. There would be another 5 in the generalization set to give the system recognizing 8 patterns. Now, if we are able to, by changing the training, by changing the system parameters, move and increase and change this generalization set so that it will recognize another set, which is the data set. And let's call that DT. Now, for a 3x3 example, you could work out the data set by taking a human, the 3x3 array, put in every possible pattern on that 3x3 array. For binary pixels, it is going to be how many? 9 pixels, how many possible patterns? 2 to the power 9, 2 to the power 9 is 512, which is the size of your universe. And you could look at those 512 patterns and take an intelligent person, better avoid mechanical engineers, but see if we can find some, and say, is this pattern a T? And so if one of the patterns were if we have that pattern, is that a T? No, so that wouldn't be in the data set. And you could actually determine the data set. So this is a trivial problem. If I go to 16 by 16 bits binary, and I wanted to assess all the patterns that were T-like on a 16 by 16 array, How long will it take? Quite some time. How long? Because on 16 by 16 by 1 bit pictures, pretty lousy resolution, can't see the details of what you're wanting to look for on your phone at 16 by 16 by 1 bit. But nevertheless, the universe will be what? 2 to the power
16 times 16.
which is 2 to the power 256, which is 10 to the power approximately 10 to the 80. And 10 to the 80 is a famous figure. The guy giving the brief lecture on artificial intelligence for radio this week used it. 10 to the 80, number of electrons in the universe. So if you wanted to sort that space out as a human to determine the data set, are these patterns T-like, it would take you a pretty long time. In fact, I would recommend don't even attempt it. Give it to a mechanical engineer. Keep them happy for the rest of their lives. So, we don't normally have the data set available to us. But what we want to do is change the system parameters. By changing the red set, it will increase the black set, and the data set is supposed to be fixed, but potentially infinite. If the black set can match the blue set, we have successful recognition. So ideally, GT, the generalization set, has got to be equal to DT. And if you can achieve that, then you've got a product, you've got potential wealth. What would normally happen is we can keep training on the red set gets bigger, the black set will get bigger, this remains fixed. We could have a situation where the black set encloses totally the data set. That's good. We're recognizing the set, but there will be some patterns which are not T-like, which will be recognized as T's. Okay, now there can be noisy patterns and whatever. That's usually not a problem. The only problem we could have by overtraining is if I have another set over here, which would be a data set, call that DB, another class. If this set, data set, wrong color, blue I was using. If I have another data set over here, let's call that DB. If this black set gets bigger and bigger and starts to encroach on another set, and supposing this black one is coming down here, we would have an area of another class of patterns which would be recognized by this. And that's the only way you can get errors on this system. Now it looks as if the universe is getting pretty crowded, but remember that universe is huge. And at 3 by 3, it's 512 points. At 16 by 16, it's 10 to the 80 points. And if you go into your super iPhone 13 resolution or whatever it is, that is the latest iPhone, isn't it? 13. Hasn't crept up another number since last night. Right. If it's i13, I don't know what's the resolution of that, 4000 by 4000. If it was just black and white, it would be a universe of 2 to the 16 billion. And if it was color, it would be 16 million to the power 16 million. Again, big data coming back to the troubles. Right, so that's the idea. And the system parameters I want to look at is, the first one is mapping. The way we connect the data to the network. In fact, I think I can remove this now, so I put it in space. Right. I want to use a training set. And the training set I want to use is one which gives a very impressive result. Now you'll have to bear with me because it needs a little bit of imagination. I want a vertical bar detector. Right. Typical training patterns are vertical bars. A vertical bar? What do you mean no?
Yes.
Yes. A vertical bar?
Yes.
A vertical bar? And we want it to be intelligent. So let's recognize slightly thicker vertical bars. Yes. And let's have another vertical bar there. We're not constraining the data. How are we doing? 1, 2, 3, 4, 5. Oh, let's recognize double vertical bars. That's vertical bar-ish. And now I want you to accept these two patterns as vertical bars. No arguing. I'm training this neural network. I'm the boss. And this is going to be a vertical bar. It's a very thick vertical bar. It fills up the whole array. Not a horizontal bar. It's a vertical bar. I say so. Yes? It's data. And the other suspension of reality is I want you to recognize this as a vertical bar. And that's so thin, it's below the resolution of pixels. Now, I'm calling it a vertical bar detector, but those are 8 patterns that you could put into that top machine. So it's possible. Right, the mapping, the initial mapping I want to take is row by row. And that will be as connected up there. Can somebody, or all of you, spend a minute thinking about that? How many entable states occur at each sampling point? And what are the 3 functions after training on those 8 patterns? The first function, we are looking at the top row. So we're looking at that in every of those, each of those 8 patterns. Convert them to decimal, that is going to be 4. What other states have we got?
2.
2, yes.
1.
Yes.
5.
Yes.
6.
Yes.
8.
Yes. 8, no. 7, yes.
0.
0, yes.
3.
3. How many states?
8.
8. How many possible states on 3 inputs?
8.
What's the contents of the memory F1?
0.
Or 1. What's the Boolean equation of F1? F1 equals 1. Now quickly, F2,
Same.
same, F3.
Same.
Every function will be 1. Every pattern comes in. The 8 training patterns. Whatever the pattern you put in, it will give an output of 1. The generalization set, therefore, is GT. Every possible pattern produces a 1. How many patterns on the 3 by 3? 2, 5, 12. 2 to the 9. So, no dash, dash, dash good. It recognizes everything. So clearly that is not, you're not going to make the millions out of that. It's just f equals 1 all the time. Now let me take the same data and change the mapping column by column. You're ahead of me. So let me change the mapping up there so you can see what's going on. And do that without ruining the column by column. So the mapping is going to be, let's put it in black. Let's have a black pen down. It is going to be 1, 2, 3. Oh, it's going to get messy. 1, 2, 3, and 1, 2, 3. Right. Don't know if that helps, but it's column by column. Right, F1. Training data. How many states?
2.
2. F2?
2.
F3?
2.
Generalization set size?
2. No. 4. 2.
How many patterns will give a 1 on F1? 2. How many patterns will give a 1 on F2? 2. How many patterns on F3? They are independent. So the total combination of inputs that will give those ones is 2 times 2 times 2, which is 8. Wow! GT equals 8. So by changing the mapping, you have completely changed the behavior of that network on exactly the same training grid. In fact, that really is, well, it's, I won't say it's NBG, but it's, I suppose, a bit like mechanical engineering. Sometimes it might be slightly useful. But what's it doing? It is recognizing, whereas this was the universe, this is recognizing 8 patterns, and 8 patterns is the training set. So it's just recognizing the training set. It will have no generalization. So by changing the mapping, we said there was 360,000 different mappings. You can't get worse than that, or higher than that in the generalization. You can't get lower than that in the training set. And all the mappings in between will give different generalizations. And again, we've got to try and map by testing whether that generalization set is matching the data set. And all you can do is, having trained the system, you keep throwing patterns which you know at it and evaluate it. Because you can't prove these systems. And going back to Elon Musk and his claims for his collision software that avoids collision in driverless cars, okay, he's evaluating it, but he's not guaranteeing it can avoid a collision, because each collision is going to be different. And he can't test on all of them, even though he claims to have tested on 500,000 smash-ups, which I don't believe, but there we are. Right, so what's in between? The third case is going to be a random mapping. Now, how are we doing for time? Right. Now, this is an example actually you can do in your own time. Mapping. Let's take the input space and I will label the pixels 1, 2, 3, 4, 5, 6, 7, 8, and 9. And the mapping I want to use is interval 1 is going to be 149. Interval 2 is going to be 726. And interval 3 is going to be what's left, 583. So, after your Christmas dinner or your New Year's party, and you want something interesting to do, take this problem, same training set, which you've got there. This is now the mapping, and the first interval will be connected to 1, 4, and 9. So going back to there, I'll draw it again. The first function, go away, we'll be looking at pixel 1, that is that, and that is that. It will be looking at pixel 4, which is there. And we'll be looking at pixel 9, which is there. And the other two fit into that zone. So, to prove for yourselves as we do this, take the same training set, test it on that mapping, see what the generalization set is. And it's, unless we are extremely unlucky, it is going to be somewhere between 8 and 512. And so you can change the generalization by looking at the match. And that gives you a possibility on a given problem to optimize the performance by connecting it to areas that are relevant to the classification. And we've got huge variability in this model. It's more like nature. The way living neurons are connected, they're not connected up randomly, they're not connected up universally. They are sampling small parts of the picture from the eye or whatever. There's not a single cell that takes every cell from the eye as an input. There'll be about 2 million. So we, I think, are getting closer to what might be natural system organization than we had with the analog one. And the training, of course, it is single pass. Tired? Yes, am I. Right. So
from
yeah.
here, what should we get? Should we get the function test we did previously?
Right. Do you want me to? Yes, I don't want to start a new topic now. This is enough, thankfully, end of term. Right. Do you want me to go through this?
Yes, please.
Right. Yes. Okie doke. 1, 4, and 9. Those are the pixels you're looking at. So 1, 4, and 9. It is going to be state 6. Yes? Anybody not see that? Speak now. If you don't, there's going to be an exam.
How is it state 6?
Pixel, what, sample 1, pixel 4, and pixel 9. These are the addresses of the pixels. 1, 4, no, 4, and 9. 1, 1, 0, and it is 6. So the second pattern, 1, 4, and 9 is 0. These are pre-play school games. Right, picture 3.
1.
1. Who said 9? How can we have 9 3 bits resolution? Next one.
2.
This one we're doing with?
Yes.
6. We've got it. No new information. This one?
1.
We've got it. Next one?
8.
7.
7.
Ah, that's a new one. This one?
7.
Got it. This one? 0. Got it. So we've only got 4 allowable states. With the column by column mapping, we had only 2 states. With the row by row mapping, we had 8. Here we've got 4. Now, if the other 2 random samplings give 4 allowable states in the middle row and 4 allowable states in the bottom row, what's the generalization set going to be? 4 in the top, 4 possibilities in the middle, 4 possibilities in the bottom. 4 times 4 times 4. Is there a genius here who can tell me what 4 times 4 times 4 is? 60 bloody 4. So check. I'm only guessing that these will give the same numbers. Check it yourself. This is just a guess to show you how, first of all, you get the number of states, and then if they work, all 4 states, then that would be the generalization set out. If these are 8 by 8, it's going to be a bigger generalization set. If these are 1 by 1, the generalization set would be just 4. No, that wouldn't happen. Okay.
Sorry, sir, the 64 is GT in this case?
Yeah. Yeah. Go back to, I've rubbed out the diagram. The training set size, you, the user, controls. The data set size comes from the real world. That's what the data is. And the generalization set is the thing that the network varies. Oh, good. Oh. Easy? Okay. 10 minutes left. Let's carry on with this. I chose this as a bit of a silly example because I wanted to get every spate on each row. Let's have a more realistic vertical pattern detector training set. Let's get rid of these. And let's take just the 3.
Sir,
Yeah.
if you had the training set to be a horizontal bar, would the column by column mapping be the universe in that case?
If the
training set
was this rotated 90 degrees,
Yeah.
then the
column by column
would be the universe, yes. Okay, guys, just for fun, just 3 training patterns. Row by row sampling. What's the size of the generalization set? Okay, too much. Function 1, the top function. How many terms? 1, 2, 3. And because it's vertical, 3 for the middle and 3 for the bottom. 3 allowable states. What's the generalization set size? 27. Okay. And if I were to test on an unseen pattern, there we are, there's a vertical bar with a bit of a squint. It hasn't been seen in the training, but that's a test pattern. What response will that pattern give? Train on this. This is the generalization set size. What response does this pattern give to the network trained on this? What are the common states?
F1, F2,
F1
and F2.
and F2.
F3.
1 and 4.
Right. Without going to the network, let's work it out from the data. We've got state 4 in the top row. Has it occurred in training?
Yes.
Yes. We've got 4 in the middle row. Has it occurred in training?
Yes.
Yes. 2 in the bottom row. Has it occurred in training?
Yes.
Yes. F1 equals F2, F3 equals 1, 3 out of 3 comes out. It recognizes it. It's the maximum score. It's never seen that pattern before. It's generalized. Wow. It has the intelligence of a foundation man. It has a generalization of the intelligence of a head of department. There you are. Right. Now let's go column by column. Okay, the same training data. Right, we're sampling now column by column, trading on this. How many states in the left-hand column?
2.
How many states in the middle column? How many states in the right-hand column? 2. Generalization set. Okay, now that doesn't really do very much because, oh yes it does, yes, 3 training patterns, 5, it's recognized 5 patterns above the training set. So now can we take this pattern, does it recognize that pattern? Right, we're looking for 6 in the first column. No, no, no. We're looking for 1. No, we're looking for 0. Yes. So go back to that model, we would get 0, 0, 1. The output would be 1. It's giving a score of 1 out of 3. Now this is where the threshold comes in. If we had a threshold of 3 out of 3, then it would not be classified. But if we had a threshold of 1 out of 3, it would be classified. So that's the second parameter, which I'm not going to talk about today. But by changing this threshold, again, for a given training set, you can independently change the size of the generalization set. So interesting things we can do with these next. Right. And let's go back. Let's put in another pattern. That's a sort of combination between horizontal and vertical. For row by row sampling on this pattern, what would be its response? Row by row?
No. No, yes.
No, yes, no.
No, yes.
So 1 out of 3. Column by column sampling?
Yes.
No, no, yes. 1 out of 3.
1 out of 3. So yes, if the threshold was set at 3, it wouldn't recognize where's the pattern gone. I've got that. It wouldn't recognize it was that pattern, wasn't it? It wouldn't recognize that as a vertical bar.
Because it's a third string.
So there it is. Which is sort of pleasing, because if I said to you as an intelligent human, is that a vertical bar or a horizontal bar? No, you had to be one of those choices. You couldn't say because it's a bit vertical and it's a bit horizontal. It's a interbar, or whatever word might be applied to the gender of that bar that's neither vertical nor horizontal. Okay, guys. 1 minute to go. Any questions? Play with these networks. They're fun. As I told you, a Brazilian student 4 or 5 years ago, he's running a university in Rio now. If any of you come from Rio and they want to do a PhD over there on digital neural networks, I'll be your examiner because I love going there. Hopefully soon you can travel again. Okay, guys. You won't see me for about a month, so don't forget me. Don't forget the work. That's the main thing. And have a good Easter, not Easter, Christmas, New Year, break, whatever it is. And don't do anything I wouldn't do. Let this go.
Thank you. Thank you.
Yeah, have a good holiday. Take care.